Dear students, in the last class we discussed optical waves are more effective in communication because of their high frequency. High frequency provides high bandwidth that leads to high information carrying capacity. But just like radio waves and microwaves, optical waves we can't send through the free space because of dust particles, rainfall, fog. Thus, we need a guided medium to guide these information carrying optical waves. That guided medium is nothing but optical fiber. We have discussed already how the signal is propagated through the optical fiber. Now, in this lecture, we are going to discuss different types of fibers. Fibers are classified based on reference profile, mode guiding, and material used. Based on reference profile, they are classified as step index fiber and graded index fiber. And based on the mode guiding, they are classified as single mode fiber and multi-mode fiber. Based on material used, they are classified as plastic core and plastic cladding. That means core and cladding both are made up of plastic. Glass core with plastic cladding and glass core with glass cladding. Our topic is classification of fibers based on the reference profile mode guiding. We are not discussing material used. Coming to the reference profile, they are classified as a step index and grain index fiber. Coming to the step index fiber, if you observe the reference profile, it shows a step nature here. So throughout the core, the reference index is uniform, that is N1. After that, there is a change in the reference index and becomes N2 throughout the cladding. So throughout the core, the reference index is N1, and yet the cladding that changes to N2. So it shows a step nature here. That's why this kind of fiber is known as step index fiber here. And if you observe this reference profile here, if 0 to A, that means A is the radius of the core. The reference is N1, and after reference becomes N2. So N1, this is the core, and this one is the cladding. So this reference profile shows a step nature. That's why it is called step index fiber. In the step index fiber, the ray path is a zigzag path here. So if the ray is entered here, then it reflects into core, and from the entering point to the core train interface travels in a right line path. Why it travels right line path? Because the reference index remains same throughout the core. At the core train interface, total internal reflection occurs, and after that it will propagate till up to core cladding interface in the straight line path. Again, it reflects back at the core cladding interface. So the ray path is a zigzag path in case of step index fiber. In case of grain index fiber, if you observe this reference profile at the core axis, the reference index is N1. From the core axis to core cladding interface, the reference index not in remains constant, varies here. That variation may be a triangle shape here, other variation may be a parabolic shape here. If it is varying as a triangle shape, that is called the triangle grade index. If it varies as a parabolic and parabolic grade index here. So if you observe the reference profile here, N of R, so N of R means it is a function of R because the reference varies with radius of the core. So 0 to A, that means from the core X to core interface, the reference changes are N of R equal to N1 into 1 minus 2 delta R by A whole power alpha. Here this delta equal to N1 minus N2 by N1. And R is the radius of the fiber, A is the radius of the core, and alpha is the reference profile constant. If alpha equal to 1, that is triangle grade index. If alpha equal to 2, that is a parabolic grade index. And after the core, throughout the cladding, the reference remains constant, that is N2. So that's why if you observe here, from the core X to core interface, there is variation in the reference X. After again remains constant. The variation may be a triangle shape or that may be parabol shape here. If alpha increases, the shape changes here. If alpha becomes infinity, that shape almost becomes a step index nature here. So this is the variation of reference profile here. There is a gradient of index along the core. So that's why it is called graded index fiber. In this fiber, the ray path is a sinusoidal path. The ray path is a sinusoidal path. Why? Because if you take the core, from the core X to core interface, what happens here? Layer to layer, the reference index decrease here. When the ray is moving from the higher reference index to lower reference index, it bend towards the higher reference index. That's why when compared with this layer is lower reference index. When compared with this layer is a lower reference index. That's why when it is moving from the higher to lower, it bend towards the higher reference index. So finally, it takes a sinusoidal path here. That's why the ray path in case of grain test fiber is sinusoidal path. So here, if you take the step is fiber here, if you observe here, this is a zigzag path here, and it is a sinusoidal path. The interesting point here is, in case of step index fiber, all the ray paths are moving with the same velocity here because the reference remains same. That's why the velocity is C by N1. If N1 is the reference of the core, the velocity to which the rays are propagating is C by N1. That's why in case of step index fiber, all the ray paths are different, but the velocity of the rays are same. That's what happens. All the rays are not reaching at the output end same time here. That's why we are getting a widening of pulse. That widening pulse is called pulse dispersion. For suppose we are sending an optical pulse like this, if you're traveling some distance, it will become like this. There is a widening of pulse takes place. That is called pulse dispersion. So if you observe in this appendix fiber here, the center green one, it traveling along the shortest path. So it reaches the output end early. And if you take the red color, that is the next shortest path. So after one, the second ray will reach the output end. And this blue color is the longest path. It reaches very late when compared with the first and second. That's why all the rays are not reaching at the output end same time. But if you observe the grain index fiber here, when the reference index observed from the core X to core line interface along the radius of the core, the reference index decreases. Reference index decreases means here the denominator, the velocity is actually C by N1. If N1 decreases, what about velocity? Velocity increases. So when the optical rays are moving nearer to the core line interface, the velocity increases. So in this case, when compared with the green, the red color ray moving with more velocity. When compared with the red, blue color ray is moving with more velocity. That's why, so when the first ray and second to third ray, if you compare here, the velocity of second one is more than the velocity of first ray, and velocity of third ray is more than the velocity of second ray. That's why what happens, all are reaching at the output and the pulse dispersion is less. So pulse dispersion is less, then we can send more bits. That means bit rate is high. Bit rate is high means information carrying capacity is high. That's why in case of step index, the dispersion is low. In case of grain index, the dispersion is high. Here, if you observe these ray paths here, each ray path can be considered as one mode. Actually, mode means we know light waves are electromagnetic waves. There is electric field and magnetic field in electromagnetic wave. How this electric field or magnetic field distribute along the its propagation direction, that tells about its mode. So mode tells about the how the field distributes along the direction of the ray propagates here. Based on that one, they are classified as transverse electric mode, TE mode, transverse magnetic mode, TM mode, and HE11 mode, that is hybrid modes. H represents the magnetic field, E represents the electric field. So here in case of optical fiber, the modes propagating is linearly polarized modes. Those are LP01 modes. If a fiber allows only one mode, that kind of fiber is called single mode fiber. A fiber allows more than one mode, that is called multi-mode fiber. So in this case, each ray path can be considered as a one mode. If you observe, this fiber allows the more than one mode. That's why it is a multi-mode, and the referent is properly step index. So this one is the multi-mode step index fiber. It's a multi-mode step index fiber. And in this case also, it allows more than one trace, means it allows more than one mode. So it is also multi-mode gray index fiber. So based on the mode guiding, the fibers are classified as a single mode fiber and multi-mode fiber. A fiber can allow only one mode, that is called single mode fiber. A fiber can allow more than one mode, that is called multi-mode fiber. So here this represents a multi-mode step index fiber. This ray path is zigzag path. This is a multi-mode gray index fiber. This ray path is a sinusoidal path. How many modes guided by a fiber? That will be decided by the V number. So the number of modes which are allowed through fiber is decided by the V number, that is also known as normalized frequency. The normalized frequency formula is the normalized frequency or V number equal to 2 pi a by lambda root n1 square minus n2 square. Here n1 is the reference of the core, n2 is the reference of cladding, and a is the radius of the core, and lambda is the carrier wavelength. And we know root n1 square minus n2 square is the numerical aperture. In terms of relative reference index, that is delta. The delta is nothing but n1 square minus n2 square by 2 n1 square. If difference is very low, the delta equal to n1 minus n2 by n1. We already discussed it in the previous class. We can write numerical aperture NA equal to root n1 square minus n2 square is equal to n1 into root 2 delta. So that's why we are replacing this root n1 square minus n2 square with 2 pi a by lambda into n1 into 2 delta. Both are representing the same value here. That is the V number. So if you want to find out the number of modes which are allowed through a fiber, first of all, you have to know it's a V number. From that V number, we can find the number of modes in case of step index is equal to V square by 2. So the number of modes through a step index fiber is V square by 2. And in case of gray index fiber, the number of modes is given by alpha plus 2 into V square by 2. And what is the alpha? Reference profile constant. If alpha equal to 1, that is step index fiber. If alpha equal to 1, that is a graded index fiber. What about single mode fiber? The single mode fiber can allow only one mode. How we can design a single mode fiber? That means the fiber can allow only one mode. Actually, the fundamental mode which can allow through the fiber is LP01. Next one is LP11. The LP11 mode cutoff V number is 2.405. So if the V number is less than 2.405, then LP11 mode also will cut off. Then what mode remains there? Only LP01. Then only one mode will be guided by that fiber. And the next mode, possible mode, is LP11. That will cut off if V number is less than 2.405. So in case of single mode step index fiber, the V cutoff value is 2.405. So if you want to design a single mode step index fiber, we have to set the parameters. What are the parameters are there? The radius of the core A and N1, N2, those are reference of core and cladding respectively, and lambda. So here A is the radius of the core, lambda is the carrier wave wavelength, N1 and N2 are references of core and cladding. We have to set the values of these parameters in such a way the value of V becomes less than 2.405. Then the fiber acts like a single mode fiber in case of step index. If you want to design a single mode grain disk fiber, the V cutoff value becomes 2.405 into 1 plus 2 by alpha whole power 1 by 2. Here again, you know, alpha is the reference profile constant. Alpha equal to 1 in case of triangle graded index, and alpha equal to 2 in case of parabolic graded index fiber. So now, if you want to design a single mode step index fiber, you have to make the value of V less than 2.405. How we can make that value less than 2.405? By changing all these parameters, either N1, N2, lambda, or A. But while we are designing any fiber, based on the conditions, we have, based on the requirements, based on the conditions, we will decide what kind of metal we are using for core and cladding. So N1, N2 values are fixed starting only. And what is the carrier wave wavelength required? That also they will decide. So that's why we can adjust the value of V in such a way the value of V becomes 2.405. That can be done by decreasing the radius of the core. So by decreasing the radius of the core, we will decrease the V number to the value less than 2.405. Then this fiber behave like a single mode step index fiber. So that's why here the core radius is around 8 to 10 micrometer diameter. The core diameter is around 8 to 10 micrometer. That means the core diameter is very, very, very less. That's why coupling the optical power into this fiber is very, very tough task. But there is no dispersion. That's why communication dispersionless occurs. That means that is required for us. So for long haul communication, always we are using single mode step index fiber. Of course, cladding from the 125 to 150 micrometer, and all the other coatings will be there for mechanical strength, all those things. But the core diameter is very, very less. That is around 8 to 10 micrometer. That is a big problem with single mode fibers because of less rate diameter. Very difficult to couple the optical power into the fiber. And in case of the single mode fiber, only one mode will travel. That mode is also through the along the X of the core, and that mode is LP01 mode. Coming to the cutoff wavelength here, we already discussed about cutoff value for V number. The cutoff value for V number in case of step index fiber is 2.405. Then by using the formula for V number, we can find out the lambda cutoff value by substituting the value of V cutoff. So here this is the V number, and this V cutoff value we know that is 2.405. Then lambda cutoff we can find out by keeping VC equal to 2.405. So take this lambda C here and VC value put it here, and the value VC equal to 2.405 if you find substitute, then we can find out the lambda cutoff. Okay, just lambda cutoff equal to this V cutoff will come here. So that V cutoff value is substitute here. Then lambda cutoff is equal to 2 pi A N1 root 2 delta by VC. That is the lambda cutoff value. Now we will compare the different fiber structures here. So now single mode step index, the core diameter around 8 to 12 micrometers. Total is 125. That is core and cladding combinedly 125 micrometer. And coming to the step index fiber multimode, the core diameter is 550 to 200 micrometer, and including cladding, that is 125 to 400 micrometer. In case of multi-mode grain disk fiber, the core diameter is 50 to 100 and cladding is 125 to 150. So if you observe these two here, this multi-mode step index and multi-mode grain index, if you observe here, observe the thickness of the cladding here, 125 to 400, but here 125 to 140. That means here the cladding thickness is very, very less also. That's why the material used for this purpose is also very, very less. And it is more effective for communication. But the problem is designing is very complicated. That's why it became more costly. Now we will compare the all the parameters here. One is reference profile. The reference profile, it will show you a step nature like this. And this is the reference profile based on the alpha value. That profile may be triangle shape or maybe parabolic shape. If alpha equal to infinity, it became a step index. When coming to the numerical aperture, root n1 square minus n2 square, this one equal to root n of r whole square minus n2 square, because the reference index of the core changes with the radius. Next normalized frequency is 2 pi a by lambda into n. I already discussed about this one. And cutoff wavelength is cutoff V value, that is normalized frequency, is 2.405 and it is 2.405 square root of 1 plus 2 by alpha. And number of modes is V square by 2 and number of modes here is alpha by alpha plus 20 V square by 2. And model dispersion we already told here. Here the dispersion is high in case of step index. Here this value is high and this value is low.